Thank you, Robin. Thank you, everyone, for having me here and for coming today. It's been a really cool visit so far. This is somehow my first time at the CCA, but I hope to come back frequently. So yeah, today I'm going to tell you a bit about how we can use the local group, of which you're seeing just sort of a movie of one of our simulations orbiting around the center, to understand dark matter and galaxy formation, and sometimes the other way around, galaxy formation and dark matter. Before I get started, I want to give a quick shout out to a huge wealth of collaborators, all these people on this slide who are all doing really phenomenal work, but there are also many other people that I didn't have space to show that comprise the entirety of the FIRE collaboration, which is, at this point, around 50 people, all of us just pooling our resources to do what I think is really great science. Excuse me. So I want to start with a primer on galaxy formation. And to my mind, the most important part of that is this pie chart, which you guys have probably all seen some version of. This is, of course, our best understanding of what the gravitating mass in the universe is. Now, I've only labeled the green section of this pie chart because that's our portion of our universe that's dark matter. And that makes up 87% of the gravitating mass in the universe, right? That's an enormous chunk of the mass. Now, dark matter, evidence says that it's only strong interactions, at least, are via gravity. We hope it has some weak interactions via other forces so that we can find it. But our zeroth order assumption is that it interacts via gravity only. Now, given how much dark matter dominates the gravitating mass, there's a very simple conclusion that comes from this, which is that gravity dominates structure formation. Fortunately, gravity, at least from a physical point of view, is very easy to simulate. We understand gravity very well. Now, the other piece of galaxy formation is, of course, the initial conditions. So this is showing you a large slice of the universe using initial conditions that are sort of extrapolated from the CMB, the cosmic microwave background. This, in particular, is an image from the Millennium simulation. High density regions are indicated by lighter colors, which you can kind of see here in the middle, and lower density regions are going to be indicated by darker colors and then by orange. And what I'm going to do is run this movie forward in time to show you what happens as gravity allows structure to form. So gravity is an attractive force, so it pulls together the high density regions here. So dark matter clumps up into what we call halos. Those halos then merge together, which you can again sort of see in the center. Smaller ones merge together to form bigger halos, and so on and so forth. And you end up with what we call the cosmic web, which looks something like this. Now, the point I want to make here is that on these large scales, this picture is phenomenally accurate, right? So any changes that we make to the large scale behavior of the universe have to still reproduce this general picture, because this general picture is correct. If we put a galaxy in each of these dark matter halos, for example, we recover this clustering of galaxies to just phenomenal accuracy. So the only real room for modifications to the picture is on small scales. So let's zoom in on this image and look at a smaller scale chunk of the universe. In particular, I'm going to pick a chunk of the universe that we think looks kind of like the chunk of the universe we live in, the local group. So here this is still pretty large scales though. So here you have a halo that we think hosts our galaxy, the Milky Way. This is roughly to scale. And of course, we have a halo that hosts our neighboring galaxy, Andromeda. Now, in order to describe those, since I've mentioned galaxies, what I need to do is describe what galaxies are, right? And in order to define galaxies, I'm going to start by showing you a few pictures of galaxies. So we know that Andromeda looks something like this. It's a nice disk. We think that the Milky Way looks something like this. Disk with clean spiral arms and a big bar in the middle. We know other galaxies sometimes look like NGC 5457 or 4414. So these have either very large extended spiral arms or sometimes much more compact arms with a big bulge in the center. Sometimes you have these enormous outflows of baryons flying out of the center of the disk, and sometimes you just have big balls of stars. But what all galaxies are is baryons living in a dark matter halo. So now that I've mentioned the term baryon, I'll come back to this pie chart. So baryons are what I call ordinary stuff. Anything that you would think of as ordinary matter is a baryon. That could be protons, neutrons, electrons, atoms, molecules, or it could be planets, stars, galaxies, or even people, dogs, cats, etc. The point I want to make here is that you need a lot more than gravity to describe galaxy formation, right? We know that all of these baryons operate under, for example, quantum mechanics, biology, right? All of these other physics that didn't enter into that previous simulation. So I want to quickly run through what some of those physics are that we think are important for galaxy formation. To do that, I really only need to focus in on one of these halos, so I'll zoom in a little bit. So we have a dark matter halo here, and I'm going to show you this not to scale, but let's walk through what we think happens when we form a galaxy. So to start off with, a galaxy turns gas into stars, so we start with some gas. Gravity causes that gas to fall into the center of the halo, but then other physics takes over. Right? So the gas shock heats, it expands under thermal pressure effectively, so roughly fills the halo. And then it's able to start cooling, so it can emit energy and lose some of that thermal pressure. Because everything in the universe is spinning, it also has angular momentum. So when this collapses down, it forms a nice disk. That disk can then further fragment and form stars. Those stars then do stuff to their environment, which we call feedback. So most importantly, you have supernovae that go off in some of these more massive stars. Those can drive those outflows that I showed you earlier before. And at the end of the day, you end up with a galaxy that looks something like this. Right? But as I showed you, galaxies also sometimes look like this, or like a big ball of stars. So the first thing I want to talk about very briefly is a project I did about a year or two ago, where we looked at what sets a galaxy's spatial size or its morphology. What sets whether it looks like that ball of stars, or looks like this big disk, or looks like something in between. So here I'm showing you a movie from one of the fire simulations. So this is looking at the stars in a galaxy that will turn out to look something like the Milky Way, right? So what we're going to do is we're going to model gas and stellar physics. So we'll model cooling, we'll model star formation, and we'll model feedback using those fire prescriptions. That means we have hydrodynamics and cooling, star formation and gas that's currently collapsing. And most importantly, we have feedback from stars, and we take those feedback prescriptions from our best understanding of the actual underlying stellar models. And then what I'm going to do here is focus solely on the galaxies that are roughly the mass of the Milky Way. So in the later part of my talk, I'll drill down into smaller systems, but for now, let's just focus on the Milky Way itself. You can see finally over here on the right, we've settled down into a nice disk-like galaxy. So the first question, of course, gravity dominates structure formation. So can we use gravity to predict the size of a galaxy? Can we say, okay, if we understand the structure of the halo, does that tell us anything about the structure of the galaxy that lives in the center of the halo? So this plot is showing you the actual size in the fire simulation of a galaxy on the x-axis, while the y-axis shows you the size that you would predict if the baryons purely follow the dark matter. In other words, if gravity is the only process that really matters for galaxy formation. And what you can see, so this dashed line is a one-to-one line, you can see that this just does a terrible job, right? You get the prediction completely wrong. So the answer is that no, gravity is not enough. You definitely need to consider other physics. So very quickly, sort of as an excuse to show you a couple cool movies, I want to talk about what we think some of those other physics are. So this movie is going to show you a galaxy that ends up almost purely a bulge, effectively no disk today. And what you're going to see, so this is showing the gas on the left and the stars on the right, and you'll see right about now, there's going to be a merger, a double merger, where two galaxies come in at the same time with nearly opposite angular momenta that very quickly funnels all the gas to the center, and you end up with a very tight, very large clump of stars, a bulge, basically. Now, at later times, you get a tiny bit of accretion around the outside that forms a gas, but that's just a small amount of the mass of the galaxy. In contrast, this galaxy is roughly a pure disk today. It effectively has no bulge at all. And what you'll see is that the gas is pretty much always coming in. There's always some fresh accretion of gas onto the galaxy. It's pretty much always prograde in the same sense as the galaxy's rotation. And there are no large galaxy mergers. So, even there, where a small galaxy flew by, it didn't directly interact with the main system itself. It just gave it some of the gas that it brought in. So our conclusion from this was that effectively the radial size or the diskiness of a galaxy, so those two things end up correlating quite strongly at Milky Way mass, is effectively set by the timing and orbit of galaxy mergers, the actual mergers that make it to the galaxy itself, not halo mergers, and to the accretion history of the gas. Now, to very quickly tie this into the Milky Way, we know that the Milky Way is relatively disk-dominated today. It has a bulge, but it also has a large disk. So that tells us that the Milky Way, at least, has had relatively smooth accretion to the present day. It's managed to keep forming stars all the way down.
Right, so there's always, for this problem, two limits. One is when you say the galaxy properties represent initial conditions, which is this one, where you say that where the radius you end up is set by the initial angular momentum. And the other limit is you say the galaxy structure is set by dynamical evolution, and the gas tends to move a lot before it settles into stars, so that there's significant angular momentum transport in disk. And my impression is this is still an open question. We don't know for the Milky Way how much angular momentum transport is, how much the disk shape is driven from that. And for these questions, well, do you believe your simulations when you get to things where you have to follow the gas for, 50 dynamical times?
I do, yeah.
Just the collapse.
I think so, yes.
Why? I mean, I don't.
Can you give me a reason why we shouldn't?
Why you shouldn't believe a numerical simulation that has too much viscous without checking? I think I would be nervous. I mean, I believe. I mean, it's.
So you're worried about the viscosity, basically.
Yeah.
I think we've done a lot of work recently in moving, particularly from SPH, which we know has problems with viscosity, to these new formulations of hydrodynamics that do a much better job of handling those types of problems. We've also run some tests with anisotropic conduction and viscosity, and we find that that has effectively no change on sort of galaxy scale properties, particularly around the Milky Way mass.
I mean, I don't worry on the time scale of 1 or 2 dynamical times when it's a formation thing, but for this question where I care about 200 dynamical times, it seems that one really would have to do sort of a rigorous set of tests in order to be convinced that this is the answer.
Yeah, I think we've done a lot of those tests. I can point you to, we have an enormous paper on physics versus numerics, basically, in galaxy formation, that I'm happy to sit down and talk through with you.
We'll talk about later.
Yeah.
But
Any other questions on? So for the rest of my talk, so far I've talked to you about what happens in the Milky Way and what happens in Andromeda. But for the rest of my talk, I want to focus on all these little tiny clumps of dark matter that you can see around the Milky Way and Andromeda, right? And the main question is what lives in these systems? Now, if those two big halos host big galaxies, it's pretty reasonable to think that those smaller halos host small galaxies, right? We call those dwarfs. So while big galaxies look something like this, look like what you think of when you think of a galaxy, dwarfs, of course, look completely different. So for example, I see nothing in this picture. I don't know if you guys do, but there is a galaxy in Draco. Draco is a galaxy. There are stars living at the center of a dark matter halo. We know that because we've measured its total mass, and it's much more mass than we can account for in the stars alone. The same is true in systems like Phoenix or Fornax or Pictoris 1. All of these systems we know are living at the center of dark matter halos. So let's talk a little bit about how dwarf galaxies form, because it's actually a bit different from how larger galaxies form. It's a unique mode of galaxy formation, I would say. So in a dwarf galaxy, well, again, we're going to start with gas. The gas is going to fall into the halo, and the gas is going to shock heat and fill the halo. But now things change. So in this case, the overall dispersion, velocity dispersion, dominates over any sort of angular momentum. So there's no real spin to this. So when the gas cools, it just falls back into the center of the halo. Then it forms some stars. Those stars pump out energy and feedback, right? But now the potential well of this halo is very shallow. So that's able to drive an enormous amount of the gas back out of the galaxy to very large radii, where the cycle can repeat. So now it cools again, it falls back into the center, forms a few more stars, and this happens over and over again. And at the end of the day, you get a galaxy that looks something like Fornax. This is not to scale. If we were to put it to scale, This will emphasize why simulating these systems is so hard, right? So Fornax has about a scale radius of about a kiloparsec. Right, so we're looking at systems that are about a kiloparsec across, so we want to resolve sub-kiloparsec scales. Now that dwarf galaxy is living at the center of a halo, which is about 50 times bigger, has a characteristic radius of about 50 kiloparsecs. That system is living in a local group-like region, which is about 50 times bigger than that. And then if you really want to do this right, which we do, then that whole thing is living is including a Milky Way and an Andromeda. These two turn out to be very expensive to simulate, so we need to stick those in there too. And then this whole thing is living somewhere in a large cosmological volume that includes all of the relevant cosmological torques important for angular momentum, for example. So this is hard. This is a very expensive problem to get right. So why do we want to do it, right? If they're so hard to simulate and they're very hard to observe because of how faint they are, why bother simulating galaxies? Why bother studying dwarf galaxies? Well, the first reason is that dwarf galaxies comprise the vast majority of galaxies in which we can observe individual stars. So that sample is effectively limited to the Milky Way, our galaxy, Andromeda, and the dwarf galaxies in the local group. Anything else, we're effectively limited to integrated light. As I showed you, or as I talked to you about, and as this movie is showing you as well, dwarf galaxies comprise a unique mode of galaxy formation. Because they're so shallow potential wells, you get this blowout reaccretion cycle that you don't really get on such large scales in Milky Way mass galaxies. I haven't shown you this, but dwarf galaxies also have the highest dark matter fractions of any objects in the universe. They're the least efficient at turning their baryons into stars. And finally, these are also the systems with the smallest objects in the universe that have dark matter, right? So if we want to study the scales of the model that are unconstrained by large-scale observations, then we necessarily want to study dwarf galaxies. And to really highlight why dwarf galaxies are worth studying, I'm going to talk a little bit about some historical tensions that have arisen at these small scales. So the first of these is what's known as the missing satellites problem. And that basically says that if we look at this picture, then we see thousands of dwarf subhalos or halos around the local group. But if we look at the observations, and even today, using all of the remarkable techniques that we've developed to find these galaxies, we still only know of about 80 or 90, right? So this is a mismatch of a factor of 10 to 100, depending on how you assign galaxies to halos. So I want to spend a little bit of time talking through some of the suggested explanations to the missing satellites problem and how my work fits into them, basically. So the first idea is that these systems are just too faint for us to see, right? Maybe we just haven't found them yet. And there's very good evidence for that. Even if you just look at the right side here, you can see that we've recently discovered a lot more galaxies than we knew of, right? Our count has doubled in about the past 10 or 15 years. This is, of course, the advent of digital sky surveys that probe a large portion of the sky to very faint depths, so you can get resolved star counts to identify overdensities and find galaxies that way. The question is, though, how many, if this is the entire explanation, then how many of these do we actually predict? Right, so there are at least some out there, but how many should we find in the future? So that was a big part of our motivation for running the original ELVIS suite that, that Robin mentioned. So this stands for Exploring the Local Volume in Simulations. This was 12 cosmological realizations of the local group. We did this work together with Kyle Lee, who at the time was an undergraduate at Chapman. He's now at SUNY, I believe. So what you can see here are just 12 of our realizations spinning around the center of the local group. And you can see all of these have a lot of structure. Of course, we have Milky Way and M31, but we have lots of small halos around them as well. Now, these are gravity-only simulations. So we have to pace dwarf galaxies into the halos according to their mass. So to do that, we turn to extrapolations of relationships that we know work at larger scales. So here where the line is solid, you can effectively derive a relationship between the total mass of a halo and the stellar mass of that halo using volume-limited galaxy counts. And you compare that with simulations where you know what the total halo mass function is. This is the abundance matching technique for the experts in the room. At lower scales, though, lower masses, volume-limited samples aren't possible, right? We don't know how many 10 to the 4 or 10 to the 5 galaxies there are in a chunk of the universe that's big enough to be statistically complete. So what we're going to do is extrapolate this relationship and test it, find out what we get, and if it matches counts down to where we think we know of galaxies, and then see what it predicts when we push further down. So I'll show you here what we call a stellar mass function. So the x-axis is the stellar mass, the y-axis is the number of galaxies larger than that stellar mass. The observations sit here, right? So as I said, we know of a little less than 100 galaxies today around the local group. If we take this relationship on the right and apply it to the ELVIS simulations, then we get, there it is, then we get these white lines here. So you can see that we're doing a great job of matching the observations down to 10 to the 5 or 10 to the 6 or so. And down here we'd say, okay, these are undetected galaxies. We predict about 1,000 of them total around the local group. That said, that's only the case if no new physics comes into play, right? So if we don't find these galaxies, and that tells us that something changes down here, and this relationship gets modified by some new physics that we're not accounting for. I also want to emphasize that you can see just from this plot how bad these galaxies are at turning their baryons into stars. So this red line here is what you would get if all the baryons allotted to each halo turned into stars, right? And you can see even at the peak, even at roughly the Milky Way scale, you're still doing a bad job. But particularly down here at the dwarf scale, the discrepancy is many, many orders of magnitude. So these things are really bad at making stars. And I'll also note, if you're interested in seeing what happens when you add scatter to this, that you can see my 2017 paper. I'm happy to talk about that offline as well. So if the answer is that these galaxies are just too faint for us to see, but they have stars, then we predict about 1,000 of them in the local group. Something like LSST should find a lot of these when it comes online in 2021. The other possibility is that these have no stars at all, right? Maybe they didn't form any stars whatsoever. The general picture there is that reionization preheats the gas, and it's then not able to cool in these tiny halos and form stars. That said, some work that I did with Coral Wheeler recently, we found that all of our all of our halos, at least 10 to the 8.5, formed at least some amount of stars. So if there is a low mass cutoff in galaxy formation, it's very low, and it's lower than we previously thought. I'll come back to this in a minute, too. Now, the other possibility is that these halos don't exist, right? So not only are there no stars in them, but they just don't exist at all. The first possibility there is that there were different initial conditions to the dark matter. What I mean there is mostly warm dark matter. So you can see in this image here, in the standard cold dark matter picture, you get lots of little tiny clumps around your central Milky Way. In a warmer dark matter picture, you eliminate all that small substructure, and you end up with just the largest subhalos surviving. Now, I'm not really going to go into why, but broadly speaking, the number of galaxies around Andromeda or the Lyman Alpha Forest, these two things tell us that dark matter is pretty cold, so it's not very likely, at least, that the missing satellites problem is solved by warm dark matter. Of course, the other possibility for why they don't exist today is that they've been destroyed by physics that are not included in these gravity-only simulations. So what do I mean by that? Well, first I want to show you this movie here from the Via Lactea simulation. This is a gravity-only simulation with no baryons, and this orange box is following, this movie up here is following this orange box, which is following a single subhalo that's orbiting around the center of the galaxy many times. Sorry, the center of the halo many times. There is no galaxy in this. On the other hand, this is a movie from the Fire simulations. You saw a satellite come in, interact with the disk. Right now we're flying through the disk, and you can see all of our dust lanes and star formation. We'll zoom out here, and what you'll see is that at the end of this interaction, there is no satellite galaxy anymore. Instead, there's this huge stellar stream that's formed because the satellite has been shredded. Meanwhile, this tiny little system that interacted with the center of the halo many, many times survived all the way down to the present day. So broadly speaking, the picture is that when you add a galaxy to the center of a dark matter halo, that galaxy does stuff dynamically, right? So on the left here is an image from a gravity-only simulation, right? And the first question we want to ask is, how big is this difference? You can see there's a lot of small subhalos around the center of the Milky Way, right? This is about a 100 kiloparsec across image. When we add baryonic physics and form a galaxy in the center of that halo, completely self-consistently, we end up with this picture. And again, I'm only plotting the dark matter density, so you don't see the actual galaxy in this image, just seeing the dark matter. So two things have changed. One, the actual central dark matter density has gone up because the baryons that form the Milky Way galaxy have pulled some dark matter in. And second, you can see all these little subhalos, particularly close to the center, they're just gone, right? They just don't survive when you add in a galaxy. Yes?
Is this by shocking?
So the answer is not really. So what we found, let me move ahead and I'll answer your question in just a second, okay? So the second question we wanted to ask was how much of this is strictly due to the Milky Way's disk, right? This image on the right, we add a lot of extra physics. We add star formation, we add gas cooling, we have galaxies in our subhalos, whereas on the left, it's just gravity only, right? So we ran a very simple test where we took that gravity-only simulation, but we added an analytic potential to the center of the galaxy. So all we did was add the gravity from the Milky Way's disk. And then we tuned that potential to closely match the galaxy that formed naturally on the right. And to my eye, these two pictures are nearly identical, right? So this tells us that most of the change in the subhalo populations is due strictly to the gravitational potential of the Milky Way's disk. That means that you're not sensitive to microphysics on galaxy scales. All you care about is galaxy mass. Now, to answer your question, we did a test where we also ran a spherical potential. So no disk shocking, because this was just a Hernquist ball, basically. And we found no change there. So our conclusion was that this was not disk shocking, but just extra tidal forces, basically. Ethan Nadler, a student at Stanford, did a really nice follow-up to this project, where he used a random forest classifier, machine learning technique, to predict which of those subhalos should survive when you add a galaxy. So here he's showing the feature scores for different machine learning models as you add additional parameter spaces to the model. And what I want to point out is that effectively the entire determination of whether a galaxy survives or not relies on its orbital properties, its pericentric distance and pericentric time, and its accretion time, when the subhalo fell into the potential of the Milky Way. In particular, the mass of the subhalo has a very small impact on this. Now, Tyler Kelly and Andrew Grouse did a really nice follow-up of this work too, where Tyler ran a lot more of these simulations with an analytic disk potential. He called this suite Fat ELVIS, P-H-A-T. That was recently published, a month or so ago. And what I'm showing you here in black are the radial distribution of galaxies that we know of. Sorry, in red, the radial distribution of galaxies that we know of around the Milky Way. In black, if you correct for sky coverage effectively. And then the colored lines are showing the radial distribution of different subhalo masses in this simulation, where more yellow basically indicates a smaller subhalo mass. So the conclusion here was that the known galaxies within about 50 kiloparsecs, roughly here, require star formation in very, very small halos. So this is, again, in agreement with what Coral Wheeler was finding, that you need galaxy formation in these tiny halos in order to explain even just the satellites we know of around the Milky Way. This also predicts, since there are a lot of subhalos at large distances, right, over 1,000 out here at 300 kiloparsecs, we should be finding these in the future, right? We ought to find a lot of tiny galaxies with LSST. So coming back to this picture, I think we can say, okay, as far as no stars at all, this is additional evidence that you need to go to very low mass in galaxy formation. So that is, I would say, unlikely until you get to very, very small subhalos. But we can definitely see that physics that are not included in gravity-only simulations are very important and are destroying a third to about a half of the subhalos that you would predict without a galaxy in the center of the halo. So there's a sort of emergent picture that comes out of this, where you say, okay, so the bright dwarfs live in the biggest surviving subhalos, right? I showed you that when we extrapolated those relationships from larger masses. and we got everything to line up nicely down to 10 to the 5, 10 to the 6. And that there are a lot of really tiny dwarfs that are undiscovered and undetected and should show up in the next generation of sky surveys. So can we test that, right? So obviously, in order to test the second portion of the statement, we're going to need large sky surveys. Those are coming, and we'll test that soon. But we can go ahead and test the first half of the statement already. We can ask, do the biggest subhalos actually match up with the bright galaxies? Now, when I say bright galaxies, I mostly mean sort of this mass range I'm talking about here, 10 to the 5 to 10 to the 8 or so in stellar mass. For someone that works on dwarfs, that's bright. And if you believe this extrapolation, then that means you're talking about total halo masses 10 to the 9.5 to roughly 10 to the 11, low below 10 to the 11. So, in order to do this test, what we're going to look at are the profiles, the actual structure of the dwarf galaxies. So here I'm going to plot the enclosed mass as a function of distance from the center of the dwarf. In the observations, we can go out, we can observe individual stars, get radial velocities for individual stars, use those radial velocities to constrain the mass of the galaxy. We can only do that at one individual radius, though, for each galaxy. So we end up with about 9 points on here. So these represent roughly the 9 brightest galaxies around the Milky Way. Now, in the simulations, we know everything. We know the complete mass profile. So we go into the simulations, and we pull out the mass profile of the biggest dwarf subhalos around the Milky Way-like, host. And those lines lie up here, right, where only 1, maybe 2 of those dwarf galaxies are actually compatible with the biggest subhalos in the simulation. Now, this is known as the too big to fail problem, or as I prefer to call it, the central mass problem, because too big to fail isn't very descriptive. And it effectively states that the subhalos that are too big to fail to form stars, the biggest subhalos around Milky Way simulations, have too much mass at their centers to host the observed dwarf galaxies around the Milky Way. Now, before I move on, I want to emphasize there are a lot of subhalos in these simulations that can host the dwarf galaxies of the Milky Way, right? But the statement cannot be inverted. There are not dwarf galaxies that can live in the biggest subhalos in the simulations, right? And nominally speaking, these are the subhalos that we expect to form the most stars. So this prediction, though, is coming from gravity-only simulations. And I could do the same type of thing I did with the missing satellites problem, where I walked through all these different types of ideas for what can solve this. Broadly speaking, I want to say what you're looking to do is either eliminate lines up here, so destroy subhalos, or move them to lower density, so effectively shift these lines down and to the right, right? That's what we're broadly trying to do in order to get the simulations, the theory, to match with the observations. Now, you can do this by changing dark matter physics. For example, you can add self-interactions to the dark matter, and you don't really have to do any sort of fine-tuning in order to make this work. But changing dark matter physics is exotic physics, and we want to, before we turn to that, we want to exhaust all other possibilities and ask, can we explain this just by adding baryonic physics, right? Can we self-consistently explain both the number and structure of dwarf galaxies around the local group with just baryons? So that motivated running the new ELVIS on Fire simulations. This is basically taking the ELVIS suite. So far, we only have a few of them, but taking the ELVIS suite and adding the fire modules, as Robin said, for star formation, feedback, etc., and letting everything run forward. Now, this is extremely expensive. So the simulation I'm showing you here, this took about 10 to 12 million CPU hours to run, right? But this is really our best option. If we want to study the dwarf galaxies around the Milky Way and throughout the local group, we have to be running these types of simulations. So broadly speaking, this is why nobody's done this yet. So let's dive into these simulations. Let's start by asking, can we reproduce dwarf galaxy counts in the local group? So first, I'm just going to count up all the dwarf galaxies that you see in this image on the left. Again, the observations lie roughly here. They're slightly different because I've chopped the x-axis at 10 to the 5. And if I go and I count up the dwarf galaxies in the picture, then I end up with a line that looks roughly like this. This simulation, we're naming Romeo, the bigger galaxy, and Juliet for the smaller galaxy. And I would argue this looks great, right? Okay, maybe we don't have sort of 2 or 3 of the biggest dwarf galaxies around the local group, things like M33 and M32 that have of order 10 to the 9 to 10 to the 10 in stars. But when you get down to smaller masses, I would say we're bang on the observations. We have a second one of these, which I'm calling Thelma and Louise. That one is also, I would argue, bang on the observations. So we're doing a really great job of producing dwarf galaxy counts. That said, we got this in the gravity-only simulations too, right? All you had to do was pick the right extrapolation between stellar mass and halo mass, and you were able to reproduce this plot on the left, no problem at all. And those simulations were a whole lot cheaper to run, right? So it's worth asking, we need to ask, can we also match the structure of these dwarf galaxies? Can we do everything self-consistently? So again, we'll turn to our enclosed mass profiles. Here you're seeing the same plot as before. This is a gravity-only simulation, picking out the biggest subhalos, plotting their mass profiles. Now, if I switch over to a fire simulation, we'll see that what we've done is we have managed to lower the density. We have managed to get rid of a bunch of these lines. We end up with curves that look something like this, right? So now, I would argue, again, we're doing a great job of matching the observations just with baryonic physics that we know exists. Don't need to invoke exotic dark matter. So I want to take a second and talk a little bit about why we're getting such excellent. Yes.
Sorry, you just bring the plot again. Just trying to understand. This is the Romeo and Juliet simulation.
This in particular is the dwarf galaxies around Romeo. Yes.
Okay. Because if I'm just looking at the galaxies above, say, 10 to the 8 solar masses, you have 3. And in the simulations, the observations have like 10.
Yeah, so this picture on the left is counting the entire local group. So satellites of M31 and field objects and satellites of the Milky Way. On the right, I'm just showing satellites of the Milky Way. So I'll come back to M31 satellites in just
Okay.
Before I talk about M31 though, like I said, I want to dive into a little bit about why we're able to actually reproduce the observations. What physics are important to reproducing these observations? Well, first, you can already see that we're well below our baryonic allotment, right? If we were to simply apply a fixed linear FBM halo to all of our galaxies, this would be way too steep and we'd way overestimate. So we're already seeing that feedback and reionization do inhibit star formation. There's also evidence, I haven't shown you, but we're seeing evidence that satellites are even less efficient than centrals in the local group at forming stars. So we think we're seeing some signs of environmental quenching as well. And finally, like I showed you in my 2017 paper, tides from the galactic disk are definitely important for shredding a lot of satellite galaxies that otherwise survive to the present day. And you saw that even in the movie I showed you. You saw a lot of systems come in and get torn apart by the central galaxy. Now, on the other hand, when we look at the central mass problem, or the too big to fail problem, well, again, tides are definitely important because they're shredding a lot of the satellites that would otherwise live up here in some cases. But we also have low baryon fractions, so that means that we reduce the overall mass of the halo. So everything sort of shifts down at fixed radius. All the lines shift down. And then finally, we do definitely see, so I showed you earlier that we had that mode of mode of galaxy formation where we gas fall in, form stars, get blown back out, fall back in, form stars, get blown back out. This bursty cyclic star formation has been shown, and we definitely do see that this produces cores in our dark matter halos, where by cores, I mean you have a lower central mass for a given fixed total mass, effectively. So you're moving mass from the center of your halo outwards. Yes?
I'm sorry, I'm just staring at this image. The observations, are you showing essentially the outer edge of those observed satellites as squares? Because they don't have profiles.
Yeah, so I'm showing the half-light radius, actually.
I'm sorry.
Yeah.
Okay, that's what I missed.
Yeah.
Thanks.
Yeah, so we can only get it at one specific radius. Excuse me. So we put all these physics together, and we're able to do a really nice job of explaining the Milky Way satellites. But I promised you I'd talk about M31 as well. So before I do, Ari?
Wait, a quick question. Did you look at the dark matter only with the disk and see what effect it had on densities?
So it doesn't have a big effect on densities, although we didn't actually put that plot in the paper. the disk effectively has an effect on counts. It just destroys a bunch of your systems. Yeah. What we found was you were pretty much either destroyed or not effective. Yeah, anything that came within about 20 kiloparsecs, gone. So, like I said, I promised I'd show you Andromeda. So here I'm plotting mass curves for subhalos around Juliet, the other host in this pair, compared with data for the Andromeda satellites. Andromeda has a lot more satellites in the Milky Way, so there are a lot more points on here, but otherwise the picture is basically the same. However, yes?
Sorry, didn't you say that Romeo was the bigger one?
I did,
So,
but it doesn't actually matter. I can flip it back.
Okay.
I could also show you Thelma or Louise. I could show you a whole bunch of other isolated ones that we've run. All of them basically have the same picture. I think, yeah, this is Juliet, but I could flip the curve. So what I want to highlight in this image, or in this plot, sorry, are actually these dwarf galaxies up here. Right? So in a gravity-only simulation, we had a bunch of curves running through this portion of the plot. When we add baryonic physics in all of our runs, so Romeo, Juliet, Thelma, Louise, or isolated Milky Ways, none of our runs have a single satellite or non-satellite central that has this much mass at this small a radius, right? So we're talking 10 to the 8 to 10 to the 8.5 at less than 500 parsecs. These are really dense systems. And our simulations are completely failing to reproduce these systems. Not only are our simulations failing to do this, but other simulations like the Apostle simulations or the Nihao simulations are also completely failing to reproduce these systems. And I also want to emphasize this mass scale, so these dwarf galaxies, I'm going to fade and change the point size here according to the stellar mass of the galaxy. What you'll see is these dwarf galaxies are ones that are about 10 to the 8 to 10 to the 8.5 in total stellar mass, right? And this is the mass scale where cores are expected to be very efficiently created, right? So this is the mass scale where you have enough stars that we think that you should really be good at forming cores in your dwarf galaxies. And we see evidence of this in for example, the ultra-diffuse galaxies around clusters, that these things look like they have been very good at pushing mass out of the center. But in the local group, this doesn't seem to be the case at all. So I would say that this is a puzzle that remains to be solved. So how much time do I have left? Perfect. So in the remaining 5 minutes, I want to quickly walk through where I think we can go next. With observations, well, the pictures, we want to go wider and we want to go deeper, basically. So ground-based, we're looking at things like LSST. I think of LSST as basically taking Keck, the best telescope in the world today, and using it to survey the southern sky every 3 nights, basically. This is what LSST will be capable of. Whether it'll actually do that remains to be determined. But yeah, this is using the best telescope in the world as a survey telescope, basically. Really awesome. Meanwhile, extremely large telescopes, 30-meter class telescopes, are going to be excellent for follow-up of LSST observations, because these reach about 10 times fainter, 10 times the light gathering power than our current best telescopes like Keck. Of course, we also have space-based missions, so JWST will fly someday, fingers crossed. I like to show this picture because, so this down here is Hubble's primary mirror, whereas this is JWST's. So this really emphasizes how good it'll be compared to Hubble. Meanwhile, WFIRST will also fly someday. I don't know the timeline on that right now. I don't know if anyone does.
2025.
Yeah, the JWST was 2015 or so.
As we, in all these projects, they have net dates, which means no earlier than.
Gotcha. So no earlier than 2025, right. WFIRST will fly. WFIRST is going to be like Hubble with an incredibly huge field of view. So I like to show this GIF, which alternates between the field of view of HST in green, all these tilings to map the disk of Andromeda, versus 2 pointings of WFIRST. Right? So this is going to be really remarkable for doing things like deep surveys from space, for example. Now, in theory land, we want to effectively add more physics to our simulations, do smarter analyses with our simulations, and ask new questions of our simulations. Right? So quickly run through a few projects that I've been thinking of and people I hope be able to collaborate with here on those projects. I think there's a wide open field in predicting the stream heating signal from the fire simulations once you account for this destruction by the disk of the Milky Way. So that might involve doing something like what Catherine's student did in this picture here. So they injected globular clusters particles that spawned tracers. Here you're seeing all the tracers of those globular cluster streams. I think maybe putting this together with the disk technique could be really powerful for predicting the signals from stream heating for these cold dark matter subhalos. I think there's a lot of work with Danielle looking at what black holes do in dwarf galaxies. I know you've been working a lot on adding AGN feedback to the fire simulations. While we know AGN are important at larger scales, we don't know what they do in dwarfs. That's an open question. I talked a little bit about with Shirley about this, but I'm very interested in some work that's going on here of using machine learning to unpack the stellar halo and figure out what galaxies actually merged into the Milky Way to create the stellar halo today. I think putting the stars into mass bin or galaxy mass bins or something like that could be really powerful and provide a really strong, stringent test of the model. And then, I showed you this discrepancy with the Andromeda high-density dwarf satellites. That could be just an observational effect. So I think it's worth doing mock observations of the simulations to make sure that we're actually getting the mass that we expect, or that the mass that we're getting actually reflects the true dynamical mass of these systems, particularly at the high mass end. I'm also interested in diving into whether there are biases in the local group environment. So these could be biases in the satellites or the centrals, the dwarf centrals. I have a paper in prep that's looking at that I'm happy to talk about with anyone offline. But it could also be biases in the actual Milky Way and Andromeda themselves. So this might involve looking at larger simulations like Illustris or doing some semi-analytic modeling of the Milky Way and Andromeda to see whether there's merger shielding or how strongly they spin up one another or don't spin up one another. I'd love to work with Catherine and Robin on the distant stellar halo of of the Milky Way and whether it overlaps with M31 at all. The two galaxies are about 750 kiloparsecs apart, with a virial radius of about 350 kiloparsecs, so they're just starting to touch. Are there effects of that? Can we find those effects? Similarly, has there been any sort of exchange of gas and stars between the Milky Way and M31? And if so, how would we actually find those? What would they show up like observationally? I'd love to work with the SMOG collaboration, which I know is largely centered here, to make better predictions for ultra-faint galaxies in local group. So we don't have the resolution to push below about 10 to the 5 in stellar mass, where I cut my plots off. If we want to look at ultra-faints, we're probably going to need to do something smart where we use higher resolution simulations of smaller volumes or of smaller galaxies and plug those results in to our bigger simulations. And then finally, I'm very interested in how we can use the local group as a time machine to understand reionization or other physics of the high redshift universe. And of course, adding new physics to the dark matter sector, particularly together with baryonic physics, which can actually act to stabilize some of those dark matter perturbations. So just to conclude, I hope I've convinced you that the local group really does uniquely constrain dark matter and galaxy formation, largely because it's the only part of the universe where we can study dwarf galaxies. I've shown you that when we run these new simulations that include known but very difficult and very expensive physics, that we're able to reproduce the bright Milky Way satellites phenomenally well. We get the counts right and we get the structures right. However, we have a lot of trouble capturing the full spread in dwarf galaxy structure, particularly around Andromeda. Finally, feel free to ask me about any of the other questions on this slide. Happy to field any questions on those, and thank you guys so much for your time.